I'm going to introduce you, for those who are not familiar, with some concepts of chemistry, and I think chemistry rules the world. Okay, when you're doing astronomy, you're talking to gods. Okay, when you're a chemist, you talk to the devil. But unfortunately, the devil has something to say, and it's worth listening. There is something that you cannot necessarily say without having a look at some constraints. And you heard a number of things about chemical oceanography of the past. You heard about the great oxygenation event. You heard about oxygen. And a lot of talks, a lot of papers we read actually play with concepts that may or may not be consistent with actual observation and with basic rule of chemistry. And I'm going to talk about a certain number of them. I'm going to talk about the state, not of the state of the art, not the state of the US, but the state of the ocean and the atmosphere in the early day of the Earth, and try to introduce some relatively simple concepts, but that literature sometimes doesn't care too much about, and sometimes it's been invented 30 years ago and people simply forgot about them, and we'll see that. So I felt that there was a need to have a word describing all the science of the ocean and the atmosphere in the past, meaning prior to, probably not the Archean, but prior to the great oxygenation event, because the situation, as I'm going to try to convince you about, is that the ocean and the atmosphere were very different from what it is today, and the simple statements about the composition of the atmosphere and the ocean are not very interesting. The first thing I'm going to talk about is the problem of water words. Okay, as François said yesterday, water words are very popular because NASA motto is if you want to go for life, you go for water. And going for water, if you have a water planet, is probably the surest thing of a failure in terms of finding life. So don't tell anybody, because it's not very popular. Everybody's going after water. And so we have this famous movie, and this is me when I was younger. And this is my summer house in here. So the point I'm going to develop is here that before 2.4, 2.7, we don't really know exactly. Most of the world was covered by water. We had a few continents. We know, for instance, we were talking about this with our group, with Emmanuel, about the Moody's in South Africa, where we know that there are continents with rivers and things like this, but this is an observation made by Nick Arndt in 1998. Oh, come on, how come all the volcanic eruptions we're seeing today, maybe Komati ice, maybe any kind of ocean floor, whatever could be observed in terms of volcanic eruptions, seem to happen under some quantity of water. We had Komati ice being erupted underwater. We had it was clearly something not very deep, but the Archean, a lot of the eruptions were, of course, the sediments. Most of sediments are deposited under a water column. So this is the kind of argument we had. Even I was young at the time when Peter Vell introduced the modern stratigraphy concepts, with the on-lap and off, all these things, all the transgression system. People thought about how inundated were the oceans. The oceans were under some, the continents actually had a coastline, and this coastline was moving, but was not moving by not much. So we have the alternating transgressions, and it was reasonably well established that what we call what we call the freeboard, I'm going to come back to this concept, hasn't evolved much around the Phanerozoic, I mean, since the Cambrian. And immediately that concept was adopted, and I was extrapolated to the Precambrian and even to the Archean. But we had no clue, actually. What was actually extremely well established for Jurassic or for the Devonian actually was not documented seriously for anything. We don't know how much of the continents were underwater or not. And so that's the concept of freeboard. The freeboard is whatever is above the water line on a boat, you know, and essentially the idea is that continents are in isostatic equilibrium and they float on top of the ocean. And there is always something rising above sea level if the density of the ship, means the continent, is actually lighter than the surrounding mantle. So this is a constraint that was used in all the models, and you can see if it's a freeboard, you're not supposed to read this, it's not important. Just to tell you that even today when I run a Google search, when I Google freeboard, I find that a lot of these classical papers are coming up, and that gives these figures that we already saw yesterday, which is the mass of continents through time, and these are very popular. They're not quite consistent. Okay, you have. Well, do I have a? Does anybody have a pointer? It works better when it's on.
Sur le côté, de l'autre côté, t'as un honor.
Oh yeah. Wow, it works. So you have all these different models of, this is the amount of crust versus time. Here's a famous paper by Reimer and Schubert. And here's the steady state model of Armstrong. But here are some other models. These ones are probably untenable in terms of freeboard. But these guys are probably, the sigmoid shapes are probably the most popular. So how can we constrain that? This is something that was right under our nose for decades. And it took a group of 3 guys, I'm sorry to say 3 French guys, but they were in Australia. Probably being far away from home helps you think. This is strontium isotopes in limestones, in carbonates. Things that we think are deposited at the bottom of the ocean, or that have been exchanging with diagenetic fluids near the bottom of the ocean versus time. So we have a strontium 8786, and when limestone or carbonate precipitate, we record the isotopic composition of strontium, which is 8786 strontium. And this ratio changes by the amount of rubidium, which is an alkali element, to strontium, which is a calcaline element. So in limestone, which is rich in calcium or magnesium, calcaline elements, we have a lot of strontium and we have very little rubidium. So the radioactive rubidium, rubidium 87, is too wimpy, too weak to influence 87 strontium, because there's already so much strontium in limestone that it's not going to change much. It's kind of freezing in time the isotopic composition of the fluids this carbonate was precipitating from, which is in general, it's a limestone, it can be dolomite, it can be calcite, it can be siderite. And what we see here, this is the strontium isotope evolution versus time, and what we see here is the evolution of the terrestrial mantle, which is this red line here. And what we see here is that with time, the difference here between the mantle and what is the ocean, which means the crust, because the You're going to hear that a lot today. The ocean is actually controlled in terms of strontium isotopes by rivers. Okay, and what we see here is that this interval between the crest, where we have a high rubidium-strontium ratio. Take a granite has K feldspars, it has micas, and the rubidium-strontium ratio is pretty high. So the relative abundance of strontium-87 moves very fast, and the ratio 87-86 gets higher and higher through time. In the mantle, the rubidium-strontium ratio, the alkali over chalcocline ratio, is fairly low. Okay, so this ratio doesn't move very fast. So we have the difference between the oceanic 87 strontium, 87-86 strontium, and the mantle value here increases through time. And the convergence point that people advocated for, it has been discussed by, this is a Shields and Weiser compilation here, and that actually goes back down to something like a 2.6, 2.7, 2.8. We don't know exactly because it's hard to find carbonates that have been preserved and didn't go through diagenesis. But overall, we can say that here we have a mantle-like seawater, and here we have a crest-like seawater. So we can explain that in a relatively simple way. What is the strontium cycle in the ocean? This is something extremely important. I have to make some level of self-citation, okay? It's, otherwise I don't look very serious. So strontium comes from the river. This is a river runoff here, and goes away into limestone. It's precipitated with limestone here. And we have a machine which is called the hydrothermal system, the black smokers or whatever, that takes the strontium from the ocean, you inject it into mid-ocean region, and is actually spouting out as a black smoker, as hydrothermal solutions here, and with the mantle value. Say here it enters, or today these fluids enter into the ridge with 87-86 strontium value of 0.709, and actually exits from the mid-ocean ridge black smokers with values of 0.703, and it's quite detectable. It's a very strong signal. So we have this machine here, and strontium, what we measure with strontium isotopes is the balance between hydrothermal activity and runoff and erosion and chemical erosion. Okay, this is if you have no continents, you're bound to have a mantle value. If there is, like today, or like 600 million years ago, 550 at the end of the Pan-African orogeny, we have a very high 87-86 strontium ratio, which means that there is a lot of chemical erosion going on, which means that for today it's Himalayas, back then it was the Pan-African mountains, and you can tell the ratio because between hydrothermal activity and chemical erosion here. So this is something that maybe it works better here. So what Nicolas Flamand and his co-workers in Australia say, well, this is not, people were talking about crustal growth. This has nothing to do with crustal growth. It's just a ratio of continents and continental presence above sea level, because to have erosion, you must have the continents being above sea level. We don't have rivers running in the ocean, okay? That's fairly obvious. And we have, what they say, it's not the crustal growth that we're seeing here. We're seeing that there is actually very little continental surface, subaerial continental surface prior to the great oxygenation event, and there is a lot of it afterwards. Continents started rising above sea level at 2.4, 2.5, something like this. So that's the beginning of erosion here, which is important here. So it has been known, and I remember I was was visiting a Gordon conference in New Hampshire, and it was still one of these living gods called Bob Garrels was advertising for this very nice picture that people tend to downplay for obscure reason here. So it's the abundance of the different rock types versus age. This is today, this is 5 billion years ago, and here you, no, this is the opposite. This is today here, and this is 4.5. No, this is age, yes, that's the age, that's today, sorry. So today we have a lot of carbonates, limestone, dolomite here. Back then, we didn't have any. That was observation made by a Russian compilation in 1964, which is actually wrong today, but not that wrong. There are some carbonates in the Archean. There are some carbonates in South Africa. There are some carbonates in Australia. But the amount of it, look seriously at the literature, the amount of it is extremely small, and they all shelf sediments. Nothing is deep, something like basin carbonates is all, that's where you find these beautiful stromatolites, okay, beautiful that John Grotzinger and other people have been describing over the years. The amount of carbonates in the past was extremely small. It means that the amount of CO3 2- in the ocean was very small. Okay, so this is a very, this is one of them here. This is John Grotzinger's picture. I mean, this student Sumner here, and you see these carbonates with structure here. Supposed to be some bugs, probably. What is it? What do you think? It's stromatolites or whatever here. Actually, when you plot the rare earth in there, you see that even these carbonates have actually, they are a mixture in terms of carbonates. There's a very nice mixing hyperbola here between detrital carbonates and hydrothermal carbonates. Even here, you can feel the hydrothermal. It smells of hydrothermal activity, even in those carbonates. This is quite funny. You can make the point very, very strongly. So we have another type of evidence, which is zinc isotopes, something done by one of our grad students, our PhD student in Lyon, and this is the zinc cycle. Zinc has isotopes 64, 66, 67, 68, and these isotopes are fractionated by a number of things, including biological activity. When they're not fractionated, so you have here zinc coming out as dissolved and detrital here into the ocean. Here it goes in estuaries. Here there are some isotope fractionation, and again we have some mid-ocean ridge hydrothermal activity. We have sedimentation here. We can make a cycle here. And when you look at the zinc isotopes between now and 4.5 billion years ago, it's actually not 4.5, but it's probably Isua is probably here. This is South Africa, this is, and what you can see, if you, this gray band here, this is age, this is now, this is then. Okay, this gray band here is detrital zinc. Zinc, the proportion of isotopes, 66 and 64, in clay minerals, in volcanic rocks, it doesn't change much. Zinc is a very essential element to life, but it doesn't change. And what you can see here is that you have a detrital component all the way to the great oxidation event, and then it takes a dip, and then it goes back up during the great oxygenation event, and goes up to a modern value, which is actually influenced by biological activity and by the fact that biological activity needs an input from continents to have some zinc so we have the first soils. That's what it's telling you here, is that the first soils are actually developing around 2.5, 2.6, the first abundant soil. Don't take me wrong. There were some continents, there were some volcanoes. But you see the difference here. You have the detrital value, it takes a dip, it goes up here. And these are manganese nodules, you know, they're pretty high. There is something else. So subaerial continents are modified by biological activity, and it shows in zinc isotopes. So what should we remember from this? Bottom line, subaerial continental expanses are much smaller in the Archean compared to today. I'm not saying that there is none, I'm saying there is less, okay? Something now which is quite obvious is the ocean, what I call the ocean factory here, where we have elements, where do they come from, where do they go, and now they go back to the first point. First, try to think about a water planet. What does it look? When we think of the ocean today, it's controlled by geology. Essentially controlled by geology. The fact that plate tectonics has broken up the Americas from Eurasia and Africa, and we have a north-south ocean, and the thermohaline circulation. This is a famous plot by Wally Broker, transcribed actually. Wally Broker died 1 or 2 weeks ago, so probably the person who influenced me the most in terms of low temperature geochemistry. And you have water sinking in the Sea of Norway, following this path here and going back at the surface here. This is the famous conveyor belt, and you see the Gulf Stream, something like the Gulf Stream here, which is, as I was discussing with François yesterday, the fact there is a Gulf Stream on the west and no Gulf Stream on the east is related to the rotation, to the spin of the Earth, and to the conservation of angular momentum, and the friction against that thing. So all these things look like this, you know. It looks so natural to us that we think of this physical oceanography in the past in the same term. But movements, actually, this is something, maybe you're going to read it, actually something that you can check. So you've taken the very nice papers by Carl Wunsch and the East Albarède, Ferrari and all these guys here from the MIT group. And they say, well, what is mixing the ocean is not thermohaline circulation. It's actually wind, wind stress at the surface. It's actually gravity wave inside. The fact that you have a different density, what you call baroclinic instability, and you start having mixing in there, you have turbulence, a vertical mixing. It is what mixes, what actually accounts for the balance of kinetic energy in the ocean, is not thermohaline circulation. The ocean are not mixed by thermohaline circulation. They're mixed by winds. They're mixed by what you call Ekman pumping, the fact that when you know that this upwelling, when the wind blows over the sea, the water goes to the right because of Coriolis forces, and then it makes some kind of a hole, and water comes back up next to the surface. So that's the detail of the mixing. So if we have an ocean word, what would so we have here the Ekman layer, which is something like 50 meters thick, where you have the effect of wind, where you can feel the effect of wind, and underneath it has to be mixed up by general circulation and by baroclinic instability in the ocean. So what would the circulation of an ocean look like? It would look like this. It would have nothing to do, it would be a zonal circulation. Remember these nice pictures of Jupiter? That's what it looks like. You know, that's in an ocean. Today it's controlled by continents. There is no continent circulation, has nothing to do. So it's mixed, but it's mixed in a very different way. And all the logic we have. So it's a very efficient mixing. This idea that you have a zone and stagnant ocean, you know, it's just nonsense. You know, people say, oh, maybe the ocean was layered. No, it doesn't. It's not layered because it's unstable. It's unstable because wind is pushing at the surface and mixes up everything. And there is some evaporation somewhere, and there is rain somewhere else. There's a different density in the water columns that creates some instability in the ocean. So there is circulation in there. So we have some things here. The main sources of elements today are what? Rivers and hydrothermal vents. We have been there already, no need to. Where are the sinks? The sinks are chemical. These are manganese nodules. These are biogenic. This is chalk. And this is detrital here. You have clays, you have flesh, you have all kinds of things. And we have a ion formation, which are chemical deposits, like cherts. Cherts in general are diagenetic, but most beef are chemical sediments. And again, We have another sink in hydrothermal vents because we inject seawater is injected into hydrothermal vents, into hydrothermal systems, and is actually exchanging with the hot basalt and is actually expelled by the system. So if we have a system with subaerial continents, a system with continents under sea level, it's extremely different. We have a calcium and magnesium carbonate forming because here there is a reaction between rain, CO2 next to the surface. We have a calcium magnesium carbonate, 87 strontium excess, as I was telling earlier. And after the 2.3 gigayears, weathering is extremely strong. Chemical weathering is extremely strong. When this guy is standing stupidly under the surface of the ocean here, there isn't much going on because there is no river. Okay? And so the essential of the chemical activity is concentrated here. So that makes a huge difference. So what do we want to remember from this? No continent, no runoff, no rivers. Well, it's a big, we have to be intelligent to say that. Hydrothermal vents must be those bringing electrolytes to the ocean. Okay. Now, the story I like. A word with a very little phosphate. The Archean had a phosphate problem. And this is what I was alluding to yesterday with Francois. Phosphate is a very useful animal. We use it. We have a nutrient. It's the master of life, essentially. This is the cycle of phosphate. You don't want to focus on this, but that there is phosphate in DNA. There is phosphate in ATP. I mean, ATP, that's the currency, energy currency of life. Rest on PO4 twice and PO4 three times. You have ADP, ATP, but it's all about phosphate because it's a most energetic reaction which is common at the surface of the Earth. So we need a lot of phosphate. No phosphate, no life. Nobody has ever been able to produce any sort of life without phosphate so far. So we have a phosphate in DNA, in ATP, and in a lot of enzymes that are critical, like alkaline phosphatases, that controls the volume of the cell and that controls the proton pump, that controls the potassium-sodium exchange. You have all the things that depend on phosphatases, and it's extremely important here. So phosphate is used massively by life. So here is nitrate, here is phosphate, and different levels in the ocean. Okay, surface ocean has essentially no phosphate. Deep ocean has a lot of phosphate. Why? Because we have energy at the surface of the ocean. We have photosynthesis, so we need a lot of new catabolism, we need a lot of metabolism, and everybody needs phosphate. So it's a nutrient, it's a limiting nutrient, life-limiting, bio-limiting nutrient. So we see that the deep water, the surface water has no phosphate, whereas deep water has a lot of it because when organic material falls down, there is always someone scavenging that material, that is repackaging phosphate and putting it back in circulation. Okay, this is absolutely obvious when you look at the cross-section of the ocean here, and you see the phosphate here. You see this is north, this is south. These are all the cross-sections of the Atlantic Ocean. You see that injection of surface water into the Atlantic, actually quite visible in the phosphate level, and it goes hand in hand with oxygen consumption. That's something which is depleted in phosphorus and which is high in oxygen. Okay, oxygen because the surface water is well ventilated. We have a lot of oxygen, but we have no phosphate. So, phosphorus cycle looks relatively simple. You derive a phosphate from continents here, and phosphate precipitates down in sediments. There is no other place to go. We cannot invent phosphate. Can we make it from other sources than continents? No. The answer is clearly no. If we today look at the input or removal of phosphate from the ocean, of the rivers. Rivers are a positive flux. They introduce phosphate into the ocean. And then people tried desperately for decades, since John Edmund in 1979 demonstrated that actually black smokers were a sink for phosphate and not a source, since other people demonstrate that low temperature alteration at the bottom of the ocean is a sink for phosphate and not a source. We have a problem. It's not something, oh, maybe people, it's not, this is an illusion, this is what I was discussing with François. Yeah, it's nothing to do with democracy, people writing that there is something, oh, maybe there is some phosphate there. No, there is none here. Zero. Okay, you can take all the votes you want, there is no phosphate coming out from the ocean floor. What do you do with this? Okay, rivers plus, submarine hydrothermal vent minus, ridge flanks minus. So what do you do with the ocean? We had a number. And don't tell me that there was a phosphatic event or all of a sudden. I took the same data as Reinhardt's, in Reinhardt's database, who was claiming that there was a rise of phosphate at the GOE. Oh, come on. Doesn't work that way. This is phosphate, percent phosphate in marine sediments through time. Where's the GOE here? You don't know, me neither. You see a continuous evolution of phosphate here through time, which indicates that little by little continents rise above the surface. This is how it works. Okay. Bottom line, no continent, no phosphate, no life. Simple to remember. So no plate tectonic, no life. Too much water, no life. Wow, we're in trouble here. Now let's talk about iron. Let's talk about the iron soup and tell you about the Archean Ocean. So far it was simple. Now it's becoming a little more complicated. Evidence of oxygen isotopes, from sulfur isotopes, demonstrated that there was no oxygen prior to the Great Oxygenation Event, not because of its name, but because of because the excess of sulfur 33, a rare isotopes, which is produced, you know, when you have natural processes going on in the ocean, on continents, whatever. Fractionation is what you call mass dependent. If you see an effect, an isotopic effect between 34 and 32 sulfur, you would expect that the effect on 33 and 32, which is the difference of mass, which is 50%, would be half of it. And it's quantum mechanics. This is something which has been verified for 70 years with no problem. So it's the mass fractionation, mass isotope effects vary linearly in principle with the difference in mass between isotopes. Here we have something else. We have a photolytic dissociation of SO2, volcanic SO2, in the stratosphere. And this is not a normal reaction with, it is something very different. You break a number of molecules and you're proportional to the number of molecules. You're not proportional. The reaction doesn't act in proportionality with the mass, it acts in proportionality with the number of molecules. So like a self-shielding in space, it's the same idea. So we start having an excess of the small guy, sulfur 33. And James Farquhar made one of probably the most significant discovery of the last decades. It's a great guy, this thing. And at 2.4, we have, until from 3.8 to 2.4, there is a mass-independent fractionation, which is due to the effect of UVs on SO2. And it tells you one simple thing: there was no ozone, because ozone is actually actually stops UV radiation. If there is no ozone, it means that there is no oxygen, because oxygen is made. You need oxygen to make ozone, so very convenient. So until and at 2.4, it comes to an end. There is no mass-independent fractionation anymore. It means that there is ozone in the atmosphere, so it means that there is oxygen. This is a very simple observation. Okay. Let's talk about another element now, which is iron in the ocean. Very simple. I told almost every single visitor last night of one thing. Iron 2 is a soluble form of iron. You know, ferrous iron. Ferric iron, iron 3, is totally insoluble. Why? Because we form, what is formed is iron hydroxide, different forms. You can have a ferrihydrite, you can have a hematite, you can have a goethite, you can have all kinds of things. But it's totally insoluble. Iron 3 is insoluble, so if the atmosphere is oxidized, iron is in the form of iron 3. If there is no oxygen, iron is in the form of iron 2+, and it's highly soluble. So today we still measure a little bit of iron. There is not much. This is a very, very small quantity in spite of what you're saying. And you see that iron is actually being emitted here by the mid-ocean ridges, by the vents here. This is a paper by Chris German. And you see that iron is emitted as iron 2 and progressively oxidized in the hydrothermal plumes in the ocean. Manganese is the same issue. Manganese actually has the highest signal-to-noise ratio. But iron is very difficult to measure, so people don't use it, but we use manganese because we can measure it very easily. So there was a time there was a lot of iron around. And you saw my rocks yesterday. You saw these abandoned iron formation. They were pretty nice. Cool. Okay. This is the largest resource for iron today. And these are different cores taken in, this is Hammersley here. This is the Transvaal. They all look more or less the same. And we had a student running, like a number of people did it before her, Fanny Thibon, measure iron isotopes, which has been measured for the last 20 years, essentially. But the idea we had was different. We want to understand the residence time of iron in the ocean back then. If you know, if an element is extremely reactive in the ocean, it's not going to stay very long. This is the issue with pollution. You know, when an element is a polluting element, and polluting because it actually enters the biological cycle, it means that it's going to disappear very quickly. If an element is of nobody's interest, let's take chlorine, sodium. Nobody cares about chlorine and sodium. I'll put some in my soup, but this is okay. It doesn't change drastically the budget of sodium and chlorine in the ocean. So these elements are actually a very long residence time because they are the guys, they're wallflowers, okay? They're left behind and so okay, you have, the idea was to measure this, and the interpretation of these banded iron formation are multiple. People have been fighting for 50 years about this, okay? And the issue is that if we want to make a, so what is a banded iron formation is largely made of magnetites. Magnetite is iron 2 plus iron 3, Fe3O4 is 1 iron 2, 1 iron 3. I told you no oxygen, all the iron is in the 2+ form. How do we oxidize iron to make iron 3? So there is a nexus electron here. What do you do with these electrons? Who wants my electron? Nobody wants it. No nitrate because there is no oxygen, no sulfate because there is no oxygen, and everything is changed to sulfur, to sulfide. There is a bit of HS minus, but this is not much, and actually precipitates as an iron sulfide. So there is no electron acceptor around. The only one, oh, life. Life, okay, we have life. So people really love this life idea about band and ion formation to oxidize the... So oxidation, the first interpretation, the oldest one by oxidation, dissolve iron 2 in deeper boiling with photosynthetic oxygen produced by cyanobacteria. Cool. Another interpretation is metabolic oxidation of iron 2 by anoxygenic phototrophs. So Garrels here, Kornhauser, Widel, life again. And then this is a bio-based interpretation. And there is something which is not bio-based, is UV photooxidation of iron 3, of iron 2. UV from the environment, breaking down water, okay, you have this reaction here, you take some H plus and you put some energy from UVs and you produce 2, and actually there is production of hydrogen. Very popular interpretation. Actually, I would say it's probably the dominant interpretation. The problem is, here we have millimoles of iron. Millimoles, okay? Tens of millimoles of iron in the ocean. It's enormous. How much H plus do we have in the ocean? In a neutral ocean, what's the concentration of H plus? What is the definition of pH? The concentration of H plus. So a pH of 7 means 10 to minus 7 H plus. So you want to oxidize 10 to minus 2 by 10 to minus 7. That doesn't sound very good. Okay? So there is a problem. So problems with 1 and 2 is biology here. The problem is that if we want to have biology, as I told you, there is nothing you can do about biology if you don't have phosphorus. There is no phosphorus in band and ion formation. There are 10 hundreds of ppm. This is nothing compared to modern sediments. There is no phosphorus, and even the sedimentation rate is very slow. We don't have a phosphorus in band formation. There is no organic activity. Oh, maybe it comes from continents. It comes from continents. No, it doesn't work, because we have a very low content of detrital components. So no aluminum, no scandium, no titanium, no zirconium, no nothing. The band and ion formation, I've been told, they work. Oh, you see the continental edge and you see a base in here. Come on, forget it. There is no aluminum. There is no detrital material. It's in the middle of nowhere. It's an ocean word. Okay, it doesn't work. You might have some volcanic eruption, a little bit of volcanic eruption. But with the amount, it doesn't work. And this is not my idea. It's been spelled out very clearly by this guy here in 1989, 1990 again, and everybody tends to forget it. Oh, he has to say that, well, but we can have a phosphate anyway. I can have a bit of aluminum anyway. No, you don't have it. It's very consistent. So, and as I told you, okay, the hypothesis number 3, not enough H plus unless the medium is fairly acidic. If you're ready to have an ocean with a pH of 2 or 3, like Coca-Cola, the Coca-Cola ocean, that's okay. You can probably, but we haven't gone that far yet. So what funny Thibon did was to actually measure iron isotopes, okay, mass of iron. What is the residence time? It's the inverse of the probability of exiting the system by unit time. If I say that one of you is living or in a room every hour, okay, this is the probability. I can tell you that the residence time is the number of people, let's say 40 here, divided by the rate of living is 1 per hour. So I can get a residence time, which is going to be the residence time of 40 hours in the room. This is the same thing. There is no secret on this. So you can calculate in a relatively simple way with the assumption that the water flux to ridges didn't change too much by more than rate of, let's forget about the change of hydrothermal activity. Let's put a factor of 2 of uncertainty on these changes in hydrothermal solutions here. This is not. So what we do essentially, we're looking for some. We have some input, and we're looking for a delta function input. We have one thing, you know, we have at some point there is a discontinuity. We introduce at one point a big amount of iron because of, for instance, a volcanic eruption. And we see how long it takes for this input to disappear in the system. We call that the E-folding time, the residence time, the relaxation time of iron. It has different words, okay? And you can see how much an iron atom spends in the ocean before it gets out of the system. So we can put some nice equation. We use the cobalt chronometer, which is the rate of an element. This element is known to actually sediment at a very constant rate. You can use that in the modern ocean very easily, and you can actually confirm that this chronometer is consistent with the other types of chronology like zircons in the ocean. So let's try. We can argue about this, but trust me, this cobalt chronometer is consistent. And we got this kind of, there should be a delta here in front of the 60 here. That's the isotopic anomaly. Here you have the scale is 0.25, it's 2, what is here, 0.15, it's 0.150, 0.15, this is a small thing. But you see the relaxation time with H here is very slow. It takes forever for iron to get out of the system. The system contains a lot of iron. So we have really an iron soup in the system. Residence time of 2 million years is here. And we can calculate with the flux, hydrothermal flux, I'll come back to this. We can calculate how much iron it makes for the ocean. We're talking about 1 to 50 millimoles of iron. So it's dark brown. It's like the lakes in Biscarrosse and all these places here. You know, they're really brown. So this is the pre-GOE ocean, contains something like 6 to 35 millimoles per kilo of iron 2+. So now let's try to be a little more quantitative, because so far it's been just playing around with numbers. And let's try to figure out what the difference between the ancient ocean and the modern ocean was. The answer is actually, you can summarize it with one word. This word is alkalinity. This is my buzzword, my own buzzword. I'm not the only one. I love it because it controls the word. So what is alkalinity? I don't know if you can read it. Can you read whatever is in red here? No. Okay. Post-GOE now. Okay. Alkalinity is the sum of sodium. It's the number of positive charges minus the number of negative charges for ions that are fully dissociated. Sodium, calcium, magnesium, whatever for cations, and you have 1 for chlorine, -1 for chlorine, -2 for sulfate. So the difference between these two guys here is called the alkalinity. It has to be equal to carbonates, the sum of charges carried by carbonates, which is HCO3 minus and CO3 2 minus. It's relatively simple. Okay, all the plus charges must balance the minus charges. Okay, that was the situation in those days. Today. Why is it important? Because if you want to, some people think, oh, I can calculate the PCO2 from the pH. Wrong. It's absolutely wrong. And you know, I got some reviews where people were saying this is, come on, give me a break. This is, so you can write all these equations here. And you you can say that PCO2 cannot be calculated from pH. Why? Because of alkalinity, and alkalinity is Wally Broker's equation. You can find them everywhere, PCO2. Don't tell me, oh, I went to Zibi's book and I used the... Okay, of course, he makes the assumption that the alkalinity is the modern alkalinity. So I have a PCO2. Of course, it's a function of the pH here, but it's also a function of alkalinity, a strong function of alkalinity. So depending on how much, I don't know if you ever tried to squeeze a lemon in the bottle of fizzy water, Perrier, for instance. You squeeze the lemon and you have all the bubbles evolving. Why? Because they're the carbonates that are dissolved as carbonates. When you see all these H plus coming, they have to go out because there is no room for carbonates. So they go out as CO2. This is very simple. Okay? But back then what was the situation? Alkaline, this one you can probably read a little better. The sum of here. What disappears? No sulfate. No sulfate, no magnesium. Magnesium goes into the rock at any temperature above 50 degrees. If you find today, we discussed that with Puri last night, if you find magnesium in hydrothermal vents, it has to be mixture with seawater or with any brine or anything like this. You put any kind of rock in contact with the solution containing magnesium, magnesium instantaneously goes into the rock. So there was no magnesium because there's no river. And here, so there is no magnesium, probably, so we left with sodium, calcium, and iron. So which is found in the absence of calcium, magnesium, sodium, the alkalinity fluxes to the ocean. So the control of PCO2 is accounted for by iron. As I like to say, banded iron formation were the ancient carbonates. So today, alkalinity is regulated by carbonates because you remove calcium, 2 charges, 2 plus, and you remove a CO3, 2 minus. So you keep the balance right. You introduce alkalinity by the reaction that François showed yesterday. You have a reaction of CO2 plus silicates or plus carbonates, and you introduce the carbonates and calcium into the ocean. You remove it by precipitating calcium and carbonates. Back then there was no carbonate, there was no... So what can we do here? What is accounting for alkalinity was iron, essentially iron. Iron and chlorine. Of course, there is chlorine here and probably HS minus. So if you try to understand what is alkalinity, this is something from my book. So the alkalinity, this is we call it in milli equivalent per kilo here. Calcium, magnesium, potassium, sodium accounts for most of it, and the negative here is sulfate and chlorine. The difference in alkalinity is the black thing is the sum here in between. Back then, all is left is sodium, iron, and chlorine. It was totally different. So don't tell me that you can say anything about PCO2 in the ancient ocean. You have no control of this. Well, find some control. So Archean iron played a modern role of calcium and carbonates today to regulate ocean's alkalinity and therefore to buffer pH of the ocean. You can calculate the amounts of, you have here, phosphate, pressure of CO2, CO3 2 minus, pH, CO3 2 minus, and this is alkalinity, okay? Depending on the alkalinity, you have a very, very different answer. By orders of magnitude, this is not a factor of 2, it's by orders of magnitude. Tell me which ions you put in the ocean, I'll tell you how much CO2 is in the atmosphere. So, what do we remember? What do we have to remember from this? Beef were the equivalent of modern carbonates. That's why there is no carbonate in the Australian in Archean record. Okay, well, we say, well, what you're saying is hydrothermal vents regulating everything, but what do we know about hydrothermal vents? We understand them very, very well, and I'm going to show it for you. I'm going to show you that. So, I promised I would. So, what's the temperature of hydrothermal vents? You know, today, most of mid-ocean ridges are between 2,500 and 3,500 meters below sea level. It's a given pressure. And forget about salt, it makes a small difference. But this is depth, this is temperature. And this is the seawater boiling point. Here you have this plot here. And a typical more pressure, the mid-ocean ridge pressure is around here. This is the critical point. So most of the boiling point are around 400 something, which is interesting. Because if you look at thermal expansion, you know, you increase by 1 degree the temperature of the environment, and you check the volume, how the volume changes with temperature. That's the thermal expansion. When you come close to the critical point, which is the case here, what's going on is that the water just expands brutally, okay? And you can see it here. This is alpha, the thermal coefficient of thermal expansion is temperature. It explodes here. That's why all the hydrothermal vents we know today erupt at temperature between 300 and 420 or something like this. It's just a matter of pressure. Temperature is controlled by pressure. This is all, okay? So this is well understood. Maybe here. The other part of the problem is what is the result of water-rock interaction? And if I take a basalt and cook it in the microwave or in the mid-ocean ridge with salty water, with seawater, what do I get? I get a rock which is called a metamorphic rock. And most of these rocks associated with hydrothermal vents are what we call in the green schist phases, temperature around 250, 300 degrees. This is green, this is boring, this is chlorite, this is epidote, this is albite, there is a reaction between seawater, and you put enough water, you have the things. And you say, well, this is complicated, I don't want to deal with this. No, people have been doing some calculations. This beautiful paper by Terry Bowers and Hugh Tell here. And this is the transformation coordinates. This is no transformation here, and this is fully transformed. Here, this is between 1% and between 5% and 100% transformation. What is the metamorphic assemblage of a metamorphic basalt? You recognize all things: chlorite, epidote, albite, paragonite, but it's a special kind of basalt here, and tremolite. It's an amphibole. So what can we do with this? We can do a lot, okay? So this is a typical mineral phases. We have chlorite, paragonite, epidote, clinozoisite, which is epidote, another form of epidote, albite, talc, tremolite. So let's write a number of equations here. What controls? You can take any reaction you want. You can write anything equation you are in between minerals and water and try to understand what's going on in the hydrothermal system. So I took some of the equations that may actually control. If you take another one, you won't change because it's thermodynamic equilibrium. If you take another mineral, you're going to get the same result. You don't care about which mineral, okay? As long as you have the temperatures determined, you have this. So this is an amphibole plus chlorite plus H plus done epidote plus silica plus water plus iron. So you're not very good at chemistry, I understand that. Are you?
No.
Okay. So you understand that when you write the equilibrium relationship, this activity of this one is a solid is 1, this activity is 1, the activity is 1, the activity is 1, and this one is taken care of in the constant of equilibrium. So essentially what we get for ferroactinolite, which is the amphibole, is essentially that iron 2 plus divided by H plus square, because we must have the same number of charges, is equal to a coefficient that depends on temperature. Do it again for calcium. Amphibole, another type of amphibole, magnesium amphibole, plus epidote, plus H plus chloride gives silica, calcium here. Well, you're right, you have an equation here, activity 1, activity 1, activity 1, activity 1, and you're left with H plus and calcium. So you get calcium over H2 plus. And you have a K, another K here, which is temperature dependent. And same thing for sodium. You can take albite, you can take actinolite. You can have a number of things like this, and you can determine one by one the equilibrium constant for all these reactions, and determine from what the geologists call the paragenesis. From paragenesis, you can calculate the composition of water as a function of the temperature. So it's good. We knew that for a number of years. And this guy, Jean Michard, in 1992, pointed out something relatively simple. He said, well, the charge balance, which is the alkalinity balance, okay? This is the iron 2 plus calcium plus sodium minus chlorine is equal to alkalinity. This guy is a small guy. Alkalinity is very small, 10 to minus 2, 10 to minus 3, 10 to minus whatever. It doesn't matter. Chlorine is 0.5. 10 to 0. So you don't care whether this one is small or not. And then you change iron 2 using the previous equations. Okay? You change iron 2, change calcium, you change magnesium, you change everything you have. And you get that kind of equations here, H plus, chlorine. What you see is that the composition of seawater is control of the hydrothermal water is controlled by two things, temperature and chlorine. Chlorine is not going to change by more than, let's say, a factor of 2, 3. We don't know how chlorine changed through time. It did change through time, okay? But we can see here that we have this equation, or we can take a complexation constant into account. But here is the log of the concentration here and log of chlorine here. More chlorine you have, the more pluses you should add to compensate for chlorine. Of course, this is why the pH is increasing. There are more H plus, magnesium increases, calcium increases, sodium increases, whatever, potassium increases here. And this is what you have here. So we know that hydrothermal vent composition could not have changed drastically because pressure and boiling temperature are determined by the depth of the ocean. And everything is controlled by the chlorine content of the ocean, which cannot have changed by orders of magnitude. Okay? We know what went into the ocean. So bottom line is that the chemistry of deep hydrothermal fluids did not change drastically through time. And now I'm going to go on to another aspect of things and try to find out what's going on with the atmosphere. And as I told you, we're in pain with finding an electron acceptor if we refuse that it has to be biological activity. But it doesn't mean that there isn't. And an obvious electron acceptor, electron exchange, is CO2 versus methane. So we can write a nice equation, CO2 plus Fe2 plus, CO2 plus Fe2 plus some water, water never hurts, gives magnetite plus methane plus H plus. And I don't know why nobody has ever calculated that reaction before. This is funny, okay? And so you have all the thermodynamic constants. So the CO2-CH4 ratio in the atmosphere, this has been published 2 months ago in EPSL, okay? And it depends on what? On iron 2 and depends on H plus. We don't care about the activity of magnetite is 1. It's a solid phase. So you can write that the CH4-CO2 ratio is actually a function of pH, the amount of iron 2 in the ocean, and some constant that you can. So what you can see here is that even minute variation of pH in the iron 2 ocean produce enormous variation of the methane to CO2 ratio. Change the pH by 1 unit. Always remember pH is a log scale, so it's a factor of 10. Change the pH by a factor of 2, okay, here. You get 6 orders of magnitude in the change of the methane CO2. This is enormous, okay? And so you can get it here. You have a pH and you have the CH4-CO3 ratio, and depending, remember, we were somewhere around here with millimoles. We're probably somewhere here. The pH is probably at 7, something like this. It means that the methane CO2 ratio in the atmosphere in equilibrium with magnetite is huge. There is essentially very little CO2 in the atmosphere. You're going to find that shocking. You say, come on, you must be bullshitting me. But no, it's not. You can tell from the equilibrium here. I had the 3 chemists checking my equations, and they say it is right. So because I was so enormous that I was kind of afraid. Above an iron ratio in the atmosphere is rich in CH4 and not in CO2. So the ocean atmosphere carbon cycle becomes very different. Modern one, CO2 in the atmosphere, it rains on continent, we have a carbonates, so we have a flux of alkalinity in the ocean, and we're losing alkalinity by precipitating calcium carbonate. We're happy with this. But back then, in the Archean, there is a CO2-CH4 equilibrium here, and precipitating magnetites. But the atmosphere is made of CH4. It has to do with the atmosphere. If there is no oxygen in the atmosphere, if we have a lot of methane in the atmosphere, there are lots of consequences. In the modern Earth, what's the fate of methane? So we have ozone here in the atmosphere, in the upper atmosphere, interacting with UVs, producing oxygen plus atomic oxygen here. H2O reacting with O and producing hydroxyl. That's what we have today. Hydroxyl, there's all kinds of reactions here, but essentially hydroxyl reacts with methane. You produce methyl first and H2O, and methyl reacts with oxygen again, and in the end you end up with CO2 plus H2O. That's why the methane residence time in the atmosphere is in the order of 10 years because it's destroyed. And so the cows can do whatever they want. Eventually their products are going to be oxidized, okay? Yeah, at the end of the line. But back then, no oxygen, what do? Oh, that's different. We have the methane here reacting itself with UVs. There is no ozone layer. Producing methyl here, but there is no oxygen to oxidize it, to bring it back to CO2. So we produce the CH3, and so we're producing, if we don't have oxygen or liquid water absent, it's the situation on Titan. And we have a CH3 reacting with all kinds of things, and we start producing ethane, we start producing all kinds of hydrocarbons, and it rains oil. You have oil lakes, oil seas in Titan. In the Earth, it was probably different because we could still produce some OH and produce some methyl here, no oxygen, liquid water present, and we still would produce a lot of methane and ethane and propane and all things like this in the atmosphere. It was raining oil. And this is an idea, this is not my idea, it's an idea by 2 famous guys, but I'm thinking Tony Lesaga and Dick Holland in the 70s, who already say, well, there must have been something like 10 meters of oil at the surface of the ocean. What do we do with this? So it is something extremely important, is that no oxygen in the atmosphere means that the atmosphere is not dominated by CO2, but is dominated by methane. And if there is methane, there is oil everywhere. And geological observation in the Transvaal, South Africa, in Australia, you find all these shelf carbonates. These shelf carbonates actually contain a lot of kerosene. as inclusions. They're wrapped in kerogen. There is kerogen everywhere associated with limestones. This is not a dream. Okay? There is a paper by Roger Buick entitled "A Massive Production of Hydrocarbons in the Archean." That was the title of his paper, 1996. So this is not a dream. So we have to make room for that kind of situation, and not the idea, CO2 and nitrogen, that's nice that's a good start for planets. No, it's not. It's not, because rocks are going to. So what can change the whole thing is if we go to small planets like Ganymedes, because the gravity is much smaller. If the gravity is lower, the composition of hydrothermal vents is going to be very, very different. The composition of the vent water is going to be very different. So it's worth today going back to these outer planets with a very small gravity field and see how they interact with the rocks, and decide what kind of chemistry we're dealing with. So it's, I think, essentially what you want to remember. The pre-GOE atmosphere was dominated by methane. It's big enough to stop there. And so I think I'm going to thank you and take a few questions before I run back home.